I can obtain like the questions, the material?
Yeah.
No, I mean like egg salad,
Yeah.
kiwi salad,
Because I
seafood
just
salad,
like, for the last week, I just obtained the
chicken salad,
second edition
ham salad.
questions.
Questions? Yeah, because that's, I mean, when it comes to the exam, the questions that are in the new book is what some of them will be on the exam, but the old ones don't do much good as far as the exam goes. But
I
yeah,
mean, I think the
content-wise,
questions just fine.
content-wise, the books, no, really aren't much different. So, should be cool. What else do I got?
So, can I see for your
No, but I can start to.
Is that the first one?
Yeah, that's
Yeah, the first, last Wednesday, but I saw like your answers and I was like, oh, like the letters. Look at the first edition book questions. Freaking paragraphs and stuff.
Yeah.
Diagrams.
I can try to throw that.
Next year will be the,
This is actually the only course I teach where the old edition of the book isn't totally okay. In physics, like when they change the book, they really don't change it at all. This one though, maybe because it's a newer book, they did change a lot as far as like the questions at the end and stuff. So you really can't use first edition book for the homework and stuff.
Yeah.
I tell all my physics classes, yeah, if you can get the older edition, go ahead, it's fine.
Well, my
This is the only one.
My good friend's gonna bring it so I can snapshot.
I was gonna say that and a cell phone camera gets you around the. Oh my gosh, it's after. Morning. Flash of activity here. I lamented before I came into class that 20 minutes ago I was in physics, and then I met with my colleague who also teaches physics, and then our department head, and then ran up the stairs. And it's been a busy 20 minutes for me in my life. What have you done in the last 20 minutes? Put that one. Yeah, see? Today, we want to continue our march through the first 3 chapters of the book. Chapter 2, homework is due today. I'll take your questions in a minute. Just with a brief reminder that next week, chapter 3 will be due, and if I'm not mistaken, the 15th, 1 week from today, we'll have that first 50-question multiple choice test. Study guides 1, 2, and 3 are where I will pull those questions from. You don't know which ones, but I will pull questions from those 3 study guides. I've given them all out at some point. If you lost yours or whatever, they're on Blackboard. And the homework assignments, chapter 1, chapter 2, chapter 3. Some of those questions will appear on your test. So pretty straightforward as to what to expect, I hope. Are there any questions about the questions in chapter 2?
Can you go over solar and lunar eclipses?
No, that is not, I didn't mean to say it so. No, I refuse. Make me. That's going to be covered in the second time we go through chapter 2. The other thing I didn't just remind you about is that we're only covering part of chapter 2 right now, the part that doesn't deal with the moon and the eclipses. We're going to save that for after the test. So don't worry about those sections. Only the part about the sun and the seasons, what we were talking about on Monday. We were showing how the sun, remember we were in Boston, and how the sun is higher in the summer and lower, and that kind of stuff. We'll continue with that a little bit today and get into some other stuff. But the moon and the eclipses, we're going to save that because that's a big part of astronomy. And the motion is even more complicated, so I want to save that part. Do you know there's an eclipse happening on Friday? And we'll be able to see it, sort of. Huh? I saw one of these news articles. It must have been a slow news day yesterday, maybe all week. It's been nothing to talk about in the news. And usually when that happens, the news, even like KDKA 6 o'clock news, they resurrect like these weird astronomy stories. I saw no less than 2 stories in astronomy on the local news yesterday. One was about how the Hubble Space Telescope took this picture of an exploding star and how remarkable it was. In a sense, yes, remarkable. wow, a star exploding out in space. Holy cow, the death of a star. The other thing, though, it's remarkable, but it's not unique. We have books full of those pictures. The news was making it out to be something new, never before seen, and holy cow, can you believe? It's a pretty picture. I won't deny, it's a beautiful image. Really cool, but there's nothing new about it. Nothing at all. I don't know, does that count as fake news? I don't know if that's fake news or not. The fact that it happens, never mind. The second one, though, they made this sensational headline. Again, I think it's these, NASA spies exploding star. That's a great headline. People are going to click on that, right? You're going to click on that and say, oh my God, a star. Well, until you realize it happens all the time. So the other one was, on Friday, there's a triple play or a triple threat or something that's happening in astronomy on Friday that makes everybody freak out. What's happening on Friday? Number one, it's the full moon. Full moon's no big deal. It happens every month, right? Once a month we get a full moon, and this one is called the snow moon. I don't know if we've mentioned it yet because we haven't talked about the moon much. Every month there's a name for the full moon. And mostly in America, we use the Native American names for the moon. Like the moon closest to the first day of fall is called the harvest moon. And then the moon that follows that is called the hunter's moon. The January moon was called, I'm going to sneeze. No, it's not called that. I'm going to sneeze for real. No, I'm not. It went away. You ever get that? Like, you think you're going to sneeze and then it goes away? Sorry. The January moon is called the cold moon. This moon, Friday's full moon, is called the snow moon. Obviously, the moons tell you something about the season that we're in. Harvest, hunting, cold, snow, right? Look at the weather forecast. Yeah, 6 inches of snow today. Some places. So that's number one. Okay, snow moon. Yeah, look, it happens every year. Don't get freaked out by the snow moon. And no, it doesn't predict the weather, no more than the groundhog does. Number two, eclipse of the moon. Yes, there will be an eclipse of the moon. Why haven't I told you about this phenomenal event? Because it's going to be a non-event. The moon is only going to go through the dimmest part of the Earth's shadow if it's not cloudy. And if you look up at the moon on Friday night, you probably won't notice anything different about it at all. But I will call your attention to it. It's called a penumbral. Write that down. What I missed? It's called a penumbral eclipse, and that signifies that the Earth's shadow will be on the moon, which you would think if the moon is in the shadow, it's going to be dark. It's not going to be that dark because of this part. That just means kind of dark. So if you look up at the full moon on Friday night, you might notice that it's not as bright as it normally is. If you can see it through the clouds, you know what I mean? It's not a thing you're gonna look at it and say, wow, that's spectacular, that's one of the coolest things I've ever seen, or gee, isn't that really neat? Not even, you might look at it and say, I don't know, it doesn't look any different to me. That's what these kind of eclipses are. They're kind of non-events. But it's gonna happen. The moon is gonna go through the Earth's shadow. And that happens a couple of times a year. And we just happen to be in the right place at the right time to see it from Pittsburgh. So that's a good thing. The weather, we can't control that, not even the groundhog. But it's the other thing that was part of the triple threat, the full moon, the eclipse, and then a comet. Astronomers are going to see a comet come roaring through the solar system on Friday night. Oh, it'll be great. And you're thinking, why hasn't my teacher told? He's a terrible person. Why would he keep these things secret? You can't see the comet. It's not bright enough unless you have a pretty nice telescope and you know how to use it. And if that's true, why are you in the introductory class to astronomy? You should be taking advanced astronomy or something. Anyway, the comet has been with us since December. It's not like it's just going to show up in the solar system on Friday. It's been with us since December. If you know where to look and you have a pretty nice telescope, you can see it. Again, a non-event, right? They're talking about Friday as like this end of the world kind of alignment of all these astronomical forces that are, the full moon, the eclipse, and a comet all in one day. Yeah, I call that Friday. It's not a big deal. These things happen all the time. There is a comet. It's been around for months. It's still going to be with us for another month before it works its way out of the solar system. And it probably won't get bright enough for you and me to see it with the unaided or naked eye. It happens all the time. Comets come and go. Only under certain special circumstances do they get bright enough for us to look up and say, wow, look, a comet. Just like the moon's eclipses. Only on rare, that's what makes them such special things. It's a rare alignment that allows us to look at the eclipse and not a penumbral, but an umbral eclipse and say, wow, that's pretty cool, or gee, isn't that special? Friday night is not going to be special. So if it's cloudy on Friday night and you're thinking you're missing out on the triple play weekend or whatever they're calling it in the news, relax. You're not missing anything, really. Sorry. Fake news. Headed sheet. Ouch. Chapter 2. Anything else? See, one question about an eclipse launched me into the diatribe against KDKA News. Christine Sorensen's getting an email from me. No, she's not. She read the story about the triple play or triple. Yes.
It was a question on the homework.
Okay. That's kind.
That was talking about if you're staying on the North Pole, where the what was it, northern
Celestial pole?
celestial pole would be.
I have a question here. Hold on. That's a good one. I can't find it. It's a good one. We're in chapter 2, right? No. I think it's. Okay, you're gonna have to help me. 23. If you're standing on the South Pole, that one.
Oh, was it that one?
No. I'm back to normal.
That's 23. I can't find the one.
It's number 4.
Number. Oh, I forgot. We're. Something's wrong. Something's wrong. Something's wrong. Right. Something's wrong. I don't know if I have all the questions. Oh, wait. Yeah, here. 4. Okay. Thank you. Start over. Chapter 2, question 4. If you were standing at the North Pole, where would you see the North Celestial Pole? Well, remember, our Earth has an equator, and our Earth has a North Pole. Look, here's the North Pole, right? That's the pivot point when you spin the globe. That's where Santa Claus lives, way up here at the top of the world, right? We live here in Pittsburgh. This blue line that runs around the middle of the globe, cuts it in half, north from south, is the equator. That's coordinates measured on the Earth, right? How far from north or south on the globe. There is also in the sky a North Pole and an equator. If you imagine, right? We always imagine that the sky is this big bubble that surrounds the Earth. It isn't real. But all the stars, the moon, the planets, everything is like somebody painted on the inside of that bubble. When we look out into space, we're seeing the paintings of all the stars around us, called the celestial sphere. If you take Earth's equator and project it outwards onto that celestial sphere that goes all around us, that's the equator of the sky, the celestial equator. The Earth has an equator, the sky has an equator. The sky's equator does the same thing that the Earth's does. It divides north from south. So there's that, right? So imagine this imaginary line, and we've talked about the celestial equator. When I was drawing these pictures of the Earth with the sun shining on it, and sometimes the sun is above the equator, and sometimes the sun was below the equator, right? What equator am I talking about then? Both. The Earth's equator and the sky's equator are the same place. It's just the same point, the same plane, technically, geometrically speaking. Well, same thing can be said for the North Celestial Pole. at a point in the sky directly out from Earth's North Pole. If I were to take this spot on the globe and find it in the sky, it would be directly over the Earth's North Pole, the North Celestial Pole. Polaris. Remember on your sky maps, the end of the Little Dipper is that little plus sign that says NCP? From Pittsburgh, the North Celestial Pole, Polaris, is about halfway up the sky. But if we went to the North Pole, the North Celestial Pole would be straight up over our heads. So the zenith. So the question says, A, zenith, B, eastern horizon, C, 23.5 degrees south of zenith. Ooh, 23.5, that's an important number. Remember, that's the tilt of the Earth's axis, but that's not what we're talking about here. D, none of the above. So, obviously A, for number 4, A. The zenith is the point directly over your head, right? No matter where you go, you have a zenith, straight up from the top of your head. Here in Pittsburgh, again, Pittsburgh is here, halfway between the equator and the pole. About 40 degrees, actually, not quite halfway. Our zenith is here. If we go straight up over everybody's head that's in Pittsburgh, we're out here on the celestial sphere. But the North Pole is where my other hand is, my right hand. The celestial, the zenith from the North Pole is the same as the North Celestial Pole. Does that make sense? This is very complicated. I'm actually teaching 2 astronomy classes this semester, and we're all going through the same thing at the same time, and I've been trying to explain this as many different ways as I can. I know it's very complicated. It's very confusing. Some of you are just kind of bewildered by it. Because it is. It's not easy. Think about, tip your hat to the people who 2,000, 3,000, 4,000 years ago were able to figure this all out on their own, right? Oftentimes we look at those ancient cultures and civilizations and say how silly and how foolish they were. They had no idea how the real world worked. Oh, yes, they did. They figured out some pretty hard problems, pretty amazing ways. One of them was this kind of stuff here, right? The fact that the Earth spins once every 24 hours, 365 days and all that. Pretty smart. Pretty smart back then. By the way, no computers back then. Right? No telescopes back then. They just watched. They just watched the sky unfold before them.
Didn't they tell the distance and how big each planet was just by its wobble? Like by observing its wobble, they could tell. Like it's.
Define wobble. Wobble's not a scientific term. It's one that I would use, but.
That's about as scientific as my brain gets, man.
What you might be alluding to is another motion that we haven't actually talked about. It's in chapter 2. It's in chapter 2. It's called precession. The scientific term for wobble is precession. As the Earth spins 24 hours a day and goes around the sun 365 days a year, it wobbles. If you watch the North Pole of the Earth, as the Earth spins, here's the North Pole, it wobbles like a top. If you take a top or a gyroscope or a dreidel or any toy that spins, a football, and spin it, it won't just spin standing up in a stationary position. It'll wobble as it spins. Is that what you're talking about?
Yes.
The wobble is actually called precession. And it's very slow. It takes the Earth 23,000 years to wobble. So we say our North Pole is pointed at Polaris. It is today. But 2,000 years ago it wasn't. 4,000 years ago it wasn't. 5,000 years in the future it won't be. Because very slowly, it's not perceptible to you and me. For you and the rest of your life, and your children, and your grandchildren, and their children, the North Pole points at Polaris. But eventually, the wobble of the Earth is going to cause the North Pole to move away from Polaris, like it was for our ancient ancestors. called precession. Can you figure out the size of the planet? Now, yes, you can, but not without physics. So I would say, if you're reading ahead like chapter 3, when they start talking, and this is if you haven't read chapter 3, this is a warning. When they start talking about Newtonian physics, the physics of Isaac Newton, that's when you can use that very subtle, you can start to infer some things about the size of a planet, the mass of a planet, things like that. So yes, to answer your question. But that came centuries after these ancient people, but still 300-400 years ago for you and me. So yeah, even before that, they were able to measure accurately the distance to these planets. Like, you ever wonder, like, how far away is Venus? How far away is Mars? And how do we know? I can show you, maybe next on Monday I can show you, but we talk more about the solar system itself. But it's really some simple geometry and trigonometry. I'm not going to make you do those calculations, of course. That's not why we're here. But it's really, if you understand geometry, you can figure out how far away the moon is. And people 1,000 years ago, 2,000 years ago, they knew how big the Earth was. And their measurements weren't that far off from what we measure today. An ancient Greek librarian, he ran the library at the ancient city of Alexandria, and he figured it out. In ancient Greece, they knew how big the world was. And by the way, they knew it wasn't flat.
I have a question about precession.
Okay.
Does that also affect the seasons as well? I mean, when it precesses?
Yeah. It moves them. We measure our seasons, and this is where we kind of left off on Monday, by the position of the sun, right? The sun is higher up in the sky, and by the way, I dropped my flashlight. Did I lose it? The sun is higher up in the sky in the summer, and we talked about how the sunlight hits the earth at a more direct angle, and that gives the earth more energy. Watch. If I need an assistant. Nope. If I take this flashlight and I shine it on the board, not like straight out from the board, but at a little bit of an angle, because remember, here in Pittsburgh, the sun never is straight up. Want to get up 60, 70 degrees in Boston, right? That's about as high as the sun gets in Pittsburgh, too. We're talking about in June and July, right, in the middle of summer. The sun is pretty high up. If I take this flashlight and shine it almost directly at the board, see the white circle of light that's coming from this flashlight? That's the energy that this light source is shining on the board. Not the great big circle, but this one. Let's see if I can do this one-handed. If I shine the flashlight here, see this circle here where the light is brightest and most intense? See? Right about like that. Let's pretend that's the energy coming from the sun on 1 square mile of Pennsylvania countryside. This is in the summer when the sun is pretty much directly over our head. But what happened? What happened? Good thing that wasn't a gun, huh? What happens in the winter? In the winter, that high angle of the sun goes away, and the sun drops to what? 20, 30 degrees off the horizon, right? So here we are again. All of the sun's energy, I'll get it back in that circle, is concentrated in that little circle. Now watch, as I move the sun to a lower angle. See how close, see how low, see how small the angle is between me and the chalkboard now? Look at this circle of light. Got much bigger. The flashlight, which is the sun, is not producing any more energy or any less energy in the winter. But what happens is the angle changes and that energy gets spread out. So instead of getting, so many watts of energy from the sun every square mile, now you're getting the same number of watts, and it might be 2 or 3 square miles. The energy from the sun in the winter per square mile is less. And where we left off, I think, was saying, does that make sense? Did that help? The days are longer, right? In the summer, sun rises earlier and it sets later. So the Earth has simply more time to soak up the sun. See, this is what I was talking about. The direction that these arrows are pointing indicate the angle of the sun. And is there a way to make this go faster?
Can you click and drag the red?
Yeah, I could, but then it just jumps around. But as the Earth goes around the sun, so now you see these arrows are going up, right? The sun is getting higher in the sky. Well, look, they're coming straight down on the Earth, and you can move your observer around. He's standing on the equator. Let's put him in Boston. That'll serve him right. There. Go to Boston. It's about Boston. Well, that's about Pittsburgh, actually. In the summer, the sun is high up here, and we're getting direct sunlight. But as summer turns to fall, the angle of the sun starts to get lower in the sky. And just like with a flashlight, you can do that get your own flashlight, do it on your kitchen table. When the sun is directly overhead, you get more energy. When the sun's rays come in slanted at an angle, you get less energy per square mile. Also, I'm going to stop it. How do I stop it? Notice how this picture shows you the globe and the daytime side of the Earth and the nighttime side of the Earth. Notice, here's the equator. Okay, that's the line we started out talking about. That's dividing north and south. Look how much more of the south is in the sunlight and how much less of the north is in the sunlight. This is day and this is night. The days are shorter in the north, in the winter time, right? Here's the day and here's the night in the southern hemisphere. They got a lot of daylight and a very short nighttime. It's warmer for them, right? So the opposite thing is true if I do jump ahead to summer. In the summer, here's the equator. In the summer, look how much daylight is in the north now. Days are long in the north, nights are short. And then the opposite is true for the south, see? So hopefully that helps. These, by the way, I have links on Blackboard where you can find these. Google's just as easy. I don't even use my own links. The University of Nebraska has these really great simulators where you can play around with this stuff. You can move your little stick figure guy all around the globe and see what summer is like in Boston, summer is like on the equator, where the zenith is at the North Pole and stuff like that. If you just search for Nebraska astronomy simulations, there's dozens of them. So you can play around with them. I would do more, but we don't have time. If this was a science class that had a lab, we could use these to do a lab. But we don't have a lab. So all we do is play with them. But it's because of the tilt of the Earth's axis. And in this figure over here, you can actually see that the Earth is tilted. There you see how the Earth is not, north and south poles are not straight up and down. The Earth is actually tilted over 23.5 degrees. That's the cause of all that. Anyway, precession you asked about. I always get around to answering these questions. Sometimes I have to build up to it. Precession does change this. In that, winter starts for us then in December. By March, it is spring. And by the end of June, it is summer, right? Those are our seasons. What happens after thousands of years and that very slow wobble? It takes winter and moves it, let's see, which way would it move it? Ahead. So winter wouldn't start until maybe January. And it would last all the way through April or May. Then summer would be July, August, and September. And then after a few more thousand years, the Earth continues to wobble some more. It shifts even further. So now winter won't start until March. And March, April, and May will be your winter months. June, July, and August will be spring. September, October, and November will be fall. The seasons do shift. It takes a long, long time. Think about the number, right? 23,500 years or something like that, right? Your lifetime is a very small fraction of that. You plus your children and your grandchildren are still a very small fraction of that number. So for the last 2,000 years, give or take, the seasons have been just about the same as what they are today. There's very little difference. There is a shift, but it's very small. It takes thousands of years to notice it, right? What's 1/4 of this cycle? 6,000 years, right? So for the months and the seasons to shift by that amount by 3 months, it takes 6,000 years. That's an awfully long time from a human perspective. But it does happen. It does happen. Other questions? Did I answer yours?
Yes.
I'm never sure because my answers take. Yeah.
Would Earth's tilt ever affect the North Pole pointing at Polaris?
Yeah, that's the other effect. There's two. I knew I should have started up my planetarium. I didn't think I needed today, but I'm glad I do. There's a point in the sky that I want to show you. It's an important point. You know when we measure, when we measure, say, latitude, right? I said that Pittsburgh is about halfway between the equator and the North Pole. And we call that your latitude, right? Well, we need a measuring point. We need a reference point to measure from. And we use the equator. We say that Pittsburgh is 40 degrees up from the equator, right? We do the same thing in the sky, right? There's different ways to measure the positions of the sun and the stars in the sky. One is called altitude. When we were playing around in Boston on Monday, we were looking at the altitude of the sun, how high off the horizon it was. There's another one, and there's another one though, that's like longitude. Are you familiar with longitude? If we measure how far you are from the equator, that's called latitude, right? Latitude. But if we want to know how far you are east and west, that's another measurement entirely. It's called longitude. And this is where we start to get into time zones and things like that. Do you know where we start measuring longitude from? Not the equator, obviously. Anybody know? The prime meridian, it's called. Prime meridian. Where is it? I'm pointing at it.
Great Britain.
Greenwich, England, Great Britain. Why is it there? Who said they get to be the starting point? That's where the Royal Observatory is. So, I don't know who started it, to be honest with you, but in England, there is a line that runs from the North Pole through the town of Greenwich, which is just outside London, all the way to the South Pole. And that's called the prime meridian. And any location on Earth is measured east or west of that spot. That spot in Greenwich, England is the start. Just like the equator measures north and south, England measures east and west. So, in the sky, we also have a spot. Let me set it up here. I want to view the equator. The sky has an equator. This red line is the celestial equator, right? You can see in February, the sun is below the equator. It's winter. Right? The sun is low in our sky. It's below the equator. Below the Earth's equator, below the celestial equator. There's also another line, though, isn't there? There's another line called the... Where'd it go? Where'd it go? Is that the right line? Yeah. Called the ecliptic. The ecliptic is this green line. It's the path, that's the one that's on your star chart at the nighttime sky. That's the path of the sun around the Earth every day. I know, the Earth, it's the path of the Earth around the sun too. Remember, it's a reflection, it's a mirror image. Now, notice these two lines are not the same thing. They are at a 23.5 degree angle, right? If I were to get a protractor from geometry class and measure this angle, it's 23.5 degrees. That's the tilt of the Earth. But they cross. Look, if I go over here just a little bit, see right here, these two lines come together. That's the point where the sun will be no longer below the equator, it'll be above the equator, right? In the summer, the sun is high above the equator, right? This is the point where they cross. This is the first day of spring, when the sun reaches this spot in the sky. Remember how we talked about right now it's in Capricorn, right? And then it's going to move over. In a month it'll be in Aquarius, and then it'll move over and be in Pisces, and then whatever comes down. The sun is continually moving, right, as the earth goes round and round the sun. When the sun hits that spot right there, that's called the Aries point. Sorry. It's called the first point of Aries, or just the Aries point, right? It's called the vernal equinox, right? That might be a term you've heard before. The first day of spring, the vernal equinox. Vernal means spring. When the sun is here today, but remember, Earth moves 1 degree a day around the sun, 30 degrees every month. So 1 month from now, the sun will shift 30 degrees this way. And then a couple more days after that, bam, it'll hit that point, the Aries point, the first day of spring, March 21st. And then from then on, the sun will be above the equator and getting higher and higher every day. But precession moves this point. Precession moves this point eastward. It's called the Aries point. Do you see? I'm sorry, I'm backwards. It moves it westward. Did I say? Wait, I'm lost. Hold on. Doesn't really matter. It's called the Aries point. Do you see the constellation Aries? It's down here. I know I got the lights on. The point where these two lines cross is right here. Let me redraw it. It's right here. Often on sky charts and things like that, it's given a symbol that looks like this. Aries is the constellation of the ram. So if you imagine like the horns on a ram, that's meant to be that symbol. So sky maps will put a dot, like they put a cross for the North Celestial Pole on your map. Sometimes they'll put a ram for the Aries point. This is the constellation Aries, the ram. It's not a very big constellation, nor is it a very bright constellation. Remember, the zodiac constellations, they're not the brightest stars, they're just the ones that are close to the ecliptic, right? That's why we know them. They're not really that bright. Why do they call this point the Aries point when clearly it's in the constellation Pisces? Remember, Pisces are the two fish? I'll try to draw a fish. There's one fish, and there's another one over here. They're joined at their tails for some reason. There's two fish that are stuck together at their tails. I don't know why, but they're called Pisces, the two fish. That Aries point is clearly within Pisces. Why is it still called the Aries point? Because 2,000 years ago, when astronomers first noticed, hey, the sun crosses the equator, it crossed in Aries. Because of the very slow, it might have been more, maybe 2,500, maybe 3,000 years ago. I don't remember who first figured this out. Because of that very slow wobble, that very slow precession, the Aries point has drifted from this point to this point, and it continues to drift today. It's moved all the way across this constellation, Pisces, and is nearing the next constellation over, which is Aquarius. This is the dawning of the age of Aquarius. The age of Aquarius. That hippie song from back in the 60s? Yeah? None of you are hippies, I see.
I'm picking up what you put down, man.
My wife always says, "You smell what I'm stepping in?" Or something like that. I don't know. My wife's a hippie, I guess. I don't know. But yeah, today, it doesn't make any sense. The Aries point is in Pisces. Not for long. Well, maybe for the next 1,000 years. Then it's going to be in Aquarius. Pretty soon, the Aries point's going to be all the way over here in Capricorn. So I think I got my seasons backwards. When I said they shift later into the year, they actually shift earlier. I knew I would get it backwards. I knew it. Pretty soon, the first day of spring will be in February. Because the sun is here today in Capricorn. Follow me? Smell what I'm stepping in? That's because of precession. Did I answer your question? What was your question again? You had a really good one.
It's more about the tilt.
Yes.
The 23 degree tilt and the North Pole pointing right at the
Okay, I knew I didn't answer your question. I knew it. We see how precession has shifted the Aries point. Now, let's forget about that and look north. Let's look north. Come on, look north. When we look north here in Pittsburgh, north, there, turn the lights out again, that little cross, right, on this chart, that's where we say the pole is today. Today, in 2017, the pole is here, about halfway up our sky, right? The horizon is right there, halfway up, there's the pole, all the way up, that's zenith. We live halfway between the equator and the North Pole, so there it is. But in the future, I'm trying to get my bearings again. In the future, well, here, let me just do this. I'll do this. Precession, pole, star. I'm guessing your intuition is exactly right here. Look at this sky chart, almost like the one I had. Here is today, right here at about 9 o'clock, right, on this chart. This is the position of the Earth's North Pole today, right next to the fairly bright star Polaris, right? But it's not going to stay there. As the Earth wobbles every 26,000 years or whatever it is, the pole is going to move away from Polaris towards the constellation Cepheus. Remember Cepheus? He looks like the little house, right? In what? A mere 4,000 years from now, the pole will be here. Notice there are no bright stars near the pole. We live, you and I, in the 21st century in an amazing time. There is no other time in our past history of the world or in the future of planet Earth where there is a star so close to the North Star, to the North Pole. Other people in other times, 5,000 years ago and 5,000 years in the future, will not speak of a North Star. Because once the pole drifts away from Polaris, it'll be pointing at an empty spot in the sky. That's what's happened at the South Pole. There is no South Pole star. There's a South Pole, but there's no star there. But as the Earth wobbles, it will come close to a couple of bright stars, but none are going to be as close as Polaris. And it will continue to wobble. All the way over here is Vega. These are more of the, if you were more familiar with the summer skies, we've been focusing on the winter skies, but Vega is a star that's in the summer, Vega and Deneb. In 10 millennia, it'll wobble all the way over here. The pole will be nowhere near Polaris.
What about in 3000 BC?
Okay.
Are there?
Yeah, this constellation that winds its way through the northern skies. It's pretty faint. It's hard to find it. It's really long and windy. It's a dragon. It's called Draco. And there's two bright red stars at the front. So it's like a fire-breathing dragon. They're like the fiery nostrils of the dragon. Anyway, all the way down here at the tail of the dragon is a star called Thuban. 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 It's a pretty close pole star. It's almost as close as Polaris, but much, much dimmer, right? Polaris is only in the top 50 in brightness. Polaris isn't the brightest star in the sky. It's not even close. Well, it's a lot brighter than any of these other stars that you might call pole stars one day. Yeah, in the year 3000 BC, so 5,000 years ago, that star was almost a pole star. Yeah. But it moved away. It moved away. And now we live in an era when, I think it was in 1999, when the pole was, mathematically as close to Polaris as it ever gets. Ever. In 26,000 years, that's as close as it ever gets. So we've already passed the point. The pole is actually slowly drifting away from Polaris. But it takes such a long time, this has absolutely no effect on your life at all. But that doesn't mean it doesn't happen. Think if you're an archaeologist and you go and you discover an ancient tomb in a pyramid in Egypt, and you're trying to decipher their hieroglyphics or whatever, and they're talking about some star near the pole. you better know that it's not the one we're looking at, because when they built those pyramids, the pole was over here, not here. Yeah. So it does affect your life if you're a historian, maybe. Did that answer your question?
Yes.
I knew I'd get there. Yeah. Probably in your book, a picture like this. I don't remember specifically because it shows the path of the North Pole. And again, if you imagine a top, hold on. I know you won't be able to see this, and I'm probably going to break your cell phone. A gyroscope, right? If I set this gyroscope to spinning on this table, I know you in the back you'll be able to see it, but watch it spin. It won't just sit there and spin around like this. As it spins, it's going to wobble. Now, this is a tiny toy. It'll wobble pretty fast. The Earth is a lot bigger and takes a lot longer to wobble, but it's the same idea. Ready? I knew I carried this around for something. Yeah, good. That's great. I can't even... Who put this string on here? There's like a cord on this... Now it's hopelessly tangled. Okay. Oh, man. Somebody put a cord, okay, somebody would have been me, on this gyroscope that's like 7 feet long. I couldn't possibly pull all that string off of there if I pulled it for a... And now it's all tangled and it's just... I can't get it out. It started to spin and then just sucked the string right up into the pivot, and now it's just hopelessly jammed. I could spend the rest of the day trying to get this out, but I won't. And now it won't spin, I don't think. Okay. Are there any other questions while I play with my toy gyroscope? Anything from chapter 2? Yeah, I can't get it to spin. There's like a cord on here that's... You only need about that much string. Why did I put 10 times that much string on there? Because I'm an idiot.
I don't know, you're the one who put it on there.
I gotta say, I cannot blame anyone else. I mean, I would sometimes, like when I try to photocopy stuff, like when I photocopied your study guides and I didn't have enough. Oh, that darn secretary! Come on, you gotta get. It's not my secretary. I do my own photocopying. Today in physics class, I wrote an equation and I wrote it wrong, and somebody pointed it out. Well, I tried to blame somebody else because I was just cutting and pasting in my notes. I'm giving up on that. And I said, well, the person when I was cut and paste, I just made a mistake. Well, no, it wasn't. It was me. I made a stupid math error. A plus sign turned into a minus sign because I'm an idiot. I'm the one that put that string on there. You're exactly right. Imagine, if you will, a gyroscope. How it wobbles. I don't have anything else that'll spin like that. I brought this whole toy box up and no spinny things. On Monday, just like I forgot my flashlight on Monday, today I'm promising you the next time I will bring a working gyroscope. I even have a great big one. Big old gyroscope. Yes?
I know this is kind of like out of the realm of like astronomy, but sort of more like towards physics.
Oh, good. That's the only two things I can show.
Okay, so you know when you spin a top
Yep.
and like it just doesn't stay like in one place.
Yeah.
It kind of like
Yeah, wanders
dances
around on you.
around. Is that a
Yeah.
byproduct of precession?
Yeah, basically the why.
Yeah.
In other words, to answer the question of why does the Earth precess? Why doesn't it just spin and stay put? It's off balance ever so slightly. In other words, all of the rocks and minerals and water and everything that makes up the Earth from here all the way into the center of the Earth is not perfectly balanced and unsymmetrical around the rotation axis of the planet. Not like this globe spins without precessing because it's balanced, it's man-made. The Earth is just lopsided a little bit. And because of the gravity of the sun, and I think this is a lot more physics than you probably want to know, I realize, but because of the gravitational pull of the sun on that lopsided mass that we call the Earth, it wobbles. Any toy that you spin is probably going to be a little bit off center, like a football or something like that, and it will precess. And even if it is perfectly balanced, if you don't set it perfectly on its pivot point, if you set it down so that it's tilted a little bit, instead of setting the gyroscope down so that it's perfectly vertical, if you set the gyroscope down so that it's tipped ever so slightly, it's going to wobble. Even if it's only 1 degree tipped, it's going to wobble. Even if it's perfectly balanced. The Earth has all those things working against it. The Earth is not perfectly balanced, and it's tilted by 23 degrees, so it's going to wobble. And it wobbles a lot. It just wobbles really slow. Word of the day, wobble. Yes.
Would the wobble be changed if, say, like natural disasters change the weight distribution of the Earth?
Yes, absolutely. Earthquakes, right? What happens when there's an earthquake? There's a shift in the land mass of the Earth. Sometimes, like there was a big one off Japan a couple of years ago, right? And these islands that are Japan moved. An earthquake literally is a shift in the crust of the Earth. And some of this Japan crust, some of this island moved. And if it moves this way or this way, it's either moving towards the pole, which is to say towards the rotation axis of the Earth, or away from it. And that makes the Earth either less unbalanced or more unbalanced, depending on which way the Earth shifts. And it can go either way, right? We never know when there's an earthquake which way it's going to go. We can't predict that kind of thing. And it changes a couple things. It changes the rate of precession. It also changes the spin of the Earth. It'll either make it spin faster or slower in some cases. It can lengthen the day, or it can speed up the day. Remember I said all days are not 24 hours? That's one reason, because the Earth is not perfectly balanced. And every time the Earth shifts, it's more unbalanced or less unbalanced. It changes. Yeah, it's crazy. They'll talk about, the effect is on the rotation is usually microseconds. So we're talking about 1,000th of a 1,000th of a second. That's how small the shift is, because continents move, but they don't move like 30 miles that way. When there's an earthquake, the Earth only shifts a very small amount. So the effect is pretty small. But if you take 1,000th of a 1,000th of a second off the rotation of the Earth for 26,000 years, yeah, it's going to have an effect. No, we were talking, that's not an observable thing. It's something that most people never give a thought to, but we've actually had an interesting discussion about it. Makes my job fun. What else? Yeah, it's weird. Go ahead.
I heard somewhere that whenever there's an earthquake, it actually affects the poles, and over time the poles actually are supposed to switch.
That's, I think, the spin axis of the Earth around the poles is pretty much set because of the way the Earth is put together and rotating. But you're talking about, I think, the magnetic pole.
Yeah.
What's weird is there are two North Poles, right? There's what we've been talking about is where the Earth, the spin axis, the rotational axis of the Earth. That's right here. But I think it's somewhere near Hudson Bay, Canada. If you know where you're talking a little bit away from Earth's North Pole. There's a point where your compass will point towards. That's called magnetic north. It's not the North Pole, but it's the point that attracts your magnetic compass. And that does change. Yeah. Sometimes, and we see this on other planets as well, even on the sun itself, sometimes the North Pole will become the South Pole. The magnetic field of the Earth will actually flip. It's done it several times in the past. It moves. The magnetic field of the Earth also moves around the North Pole and even goes all the way over. We know that because we can look at rocks from deep down in the Earth's crust, and the Earth's magnetic field is trapped in those rocks. In other words, when those rocks were laying on the surface of the Earth and first being formed by molten lava or whatever, their magnetic properties were trapped within them when they solidified. And when you dig up a rock that's buried in the earth for 40,000 years, you see what the Earth's magnetic field was like 40,000 years ago. And in many cases, vastly different than what it's like today. Sometimes, like I said, even upside down. We know that your compass points north. Sometimes compasses point south. And I don't mean today or yesterday. I mean 40,000 years ago, maybe it pointed south. You know what I mean?
Would the planet actually flip, or is
No.
it just the pole?
Geographically, or rotationally, or however you want to describe the Earth's place in space, that doesn't change. Even the continents and all that. Just the magnetic field. So again, the only way you'd be able to tell is with a compass. Yeah. It's a thing called, I forget the name of it, doesn't matter. When you, say you're a pilot, and you're flying a plane but with a compass, you have to know that if your compass tells you you're flying north, you're not really flying north. You're flying towards Hudson Bay, not towards the North Pole. So pilots have to be able to adjust. Now, computers have solved a lot of those problems for us. But pilots have to be able to adjust from what's called true north to magnetic north so they can navigate by compass. Because what do you do if you're in that airplane and your computer goes down? Happens. It also varies depending on where you are on the planet. Not every place has the same deviation between magnetic north and true north. So sailing a ship or anytime you're navigating by compass, you have to account for the fact that it's different. And I was going to say, if you have a car, a relatively new car, and you have a compass in your car, like on the dashboard, or maybe in the rear view mirror, there's a little thing that tells you what direction you're going, that has to be calibrated based on where you live. You actually have to go into the settings in your car's compass and calibrate it so that it knows the difference, because it's a magnetic compass. It's going to follow the magnetic field of the Earth. That's not where the North Pole is. So you actually if you live in California, or if you live in the middle of the country, or if you live on the East Coast, you have to make a setting adjusting the compass in your car. I know, you all navigate by compass every day in your car, right? I've always wondered, why do cars have compasses? But a lot of they do. Every car you buy today pretty much has a compass in it. Why?
Well, not everywhere has cell service where you can get like vehicle maps.
Okay. Okay.
Well, there's also GPS compasses too.
Now those are going to tell you where north is by satellite. So an interesting experiment. I use the word interesting relatively. But hey, now that football season's over, what else do you have to do? NASCAR won't start for 2 more weeks. So you got 2 weeks. Find a magnetic compass and find a GPS unit. Either your car, if it has navigation, or if you have a cell phone that has GPS in it, compare them. Compare them. See if you can see the difference between where the satellite tells you north is, because the satellites are going to go by the North Pole. But if it's a magnetic compass, it's going to point to a different spot. It's going to be off by, I think in Pittsburgh, it's off by 8 or 10 degrees. I forget the actual value for here. I haven't calibrated the compass in my car lately. They're off. They're off. If your cell phone will tell you where north is, but a compass won't. Ha!
Does the magnetic field have anything to do with the northern lights?
Yes, entirely. We'll get that's a really complicated scenario, and we'll get into that more because we have to talk about the sun first. The northern lights come from the sun, believe it or not. The interaction of the sun and our magnetic field is what stirs up the northern lights. Aurora, we call that the aurora. Yep. And since the magnetic field changes, don't you know, where you can see the northern lights changes. Now again, these changes, it's weird. I always thought it was weird studying classes like geology and things like that, where you're studying things that happened 100,000 years ago. And it's almost like, I guess, people have the same problem in astronomy when you're trying to talk about distances of 100 million miles. Who can comprehend that? I can't comprehend 100 million miles, just like I can't comprehend 100,000 years. But that's the kind of stuff we're talking about. The time it takes for precession, the time it takes for the changes in the magnetic field, it's not a human lifetime. It's much bigger than that. I guess I have a small mind. Is that what I just said? I'm the one that can't use a gyroscope. I don't know if you noticed. Fail. What else? The Aries point is something that we haven't talked about, but it's an important marker. It is the point. It's if you're thinking about latitude, longitude, right? That tells you where you are on Earth. The analogy is perfect. Your latitude and your longitude tell you where anything is on the surface of the Earth. You measure north or south from the equator. You measure east or west from England, Greenwich. In the sky, we have coordinates too. One is north or south of the equator. That's pretty obvious. It's called declination, just like latitude does. The other one, though, how do we know how far east or west things are in the sky? We have a point that we use to measure from. It's called the Aries point, and I'm nowhere near. The Aries point, where the equator crosses the ecliptic. It crosses again, right? The Aries point is in Pisces. The Aries point is here. That's the first day of spring. But guess what? The sun crosses the equator not once, but twice. I think that's one of the questions. The sun crosses the equator, obviously, twice. Once here, and if we keep following these two lines, hey, there's the moon, around the sky, they come together again. Now, when the sun, remember, the sun keeps marching this way, east. The sun will drop below the equator here. This is the first day of fall. This happens on September 21st. That's the first day of fall. That point doesn't have a special name like the Aries point. It's just a spot in the sky because we don't measure anything from there. It's just the other side of the globe. It's like being on the other side of the globe from England. Where are you? You're on the date line, actually. It's the international date line. But this point has no real significance. But know that in the summer, the sun is above the equator. In the winter, it's below the equator. And when they cross, it's called an equinox.
Is that the same thing as a solstice? Or
So there's those terms, right? When we have an equinox, yeah, the term means equal night. Equal night. The sun is in the middle of the sky. That is to say, the sun is on the equator. Remember, it happens twice. Once in the spring, March, once in the fall, in September. The sun is on the equator. So that means how the days are longer in the summer, daytime is longer in the summer and shorter in the winter. But on these days, it's not longer or shorter. It's in the middle. We get 12 hours daylight, 12 hours darkness. It's equal on those 2 days. So you've noticed the days are getting longer, right? The sun stays out later at night. It's now 5:30, 5:45, 6 o'clock by the time it gets dark outside. By the time the equinox comes along, it'll be 6 o'clock or a little bit later. But you gotta be careful because by then we'll be on daylight savings time. We talked about what a mess that is, right? It'll actually be 7 o'clock, not 6 o'clock. But you get the idea. That's these days, right? When we're in the middle. The extremes of the seasons, when the sun is at its highest point, or when the sun is at its lowest point, high above the equator, far below the equator. I can find that spot in the sky for you too. If I'm getting seasick, maybe I can. It won't let me turn it around though. Notice, I know the lights are on, but notice how far above. There's that green line. That green line is the ecliptic, and this red line is the equator. This is summer, right? When the sun is way up above the equator. At its highest point, that angle is 23.5 degrees. The sun is 23.5 degrees above the equator. Does that number sound familiar? It should. That's called a solstice. This is great. I can't spell it. I think that's how you spell it. Sol, sun, right? Sol means sun. Stis. It means stands still. The sun stands still. On the summer solstice, halfway between the equinoxes, June 21st, in other words, right? That day. Remember when we were in Boston on Monday, at least virtually? Every day, or every month, I was writing the numbers up here. As the sun got higher and higher and higher and higher in the sky, I kept writing those numbers down. It went like 32, 45, 50, 60, 70, right? But you notice June and July, the sun didn't move. Remember? It got up to about 70 degrees up there, but then in June and July it didn't move. The sun stood still. Solstice. The ancient people saw that. They said, hey, look, the sun's getting higher and higher. Every day, the sun's getting higher. And then comes June, and it stops getting higher. And you wait, and it just, there it is, every day. In July, there it is, every day. The sun stands still. It's on that, I almost said the wrong word again. It's on that ecliptic, but it's far up as it's going to get, and then it starts to come back down towards the equator again. August, September, the sun is sinking until you get to September 21st, equinox. We're in the middle. And then the sun, October, November, sinking, lower and lower below the equator until you get to December 21st. That's another solstice. The sun stops dropping, stands still for a while, and then comes back up again. So December, January, the sun's not moving up or down again. It's standing still. It moves a tiny little bit every day, but not noticeable. And then January, February, March, now the sun is on the move back north again, back up. March, we hit the equinox. So equinox, equal nights. That's the first day of fall and the first day of spring. Solstice, when the sun stands still, that's the first day of summer and the first day of winter. Those are the extreme points, the highest point and the lowest point of the sun. It takes a lot, a whole lot. How long have we've been, 3 weeks, 4 weeks? How long is this class? To get in, and I sound like a hippie, to get in tune with these motion of the stars in the sky, right? We're tuned in to the cosmic vibe. No, I hope we're understanding these motions. They're very subtle. Remember, there's a lot happening. The sky shifts 1 degree per day, which isn't much, but after a month, the whole sky has shifted 30 degrees. That's because the Earth goes around the sun. Every day from January, February, March, the sun creeps higher in the sky. Not much, but after a month or 2 months, the change is noticeable. The days are longer, the days are warmer, the seasons are happening. And then there's that whole precession thing that just, you won't notice it ever because you won't live that long. Hope that's not shocking news to anyone. You won't be here 20,000 years from now. But there's another motion that affects, the coming and the going. If you put all that together, that's an enormous thing to behold. You're in tune. You know what I mean? You know, at this point, maybe it's not all clear how it all fits together. Maybe you're still thinking like, this doesn't make any sense. But I think if you start to think in these terms and what they mean, and I've shown you with these pictures how they move, right? Yeah. Questions? What? Let me show you one more thing. I don't want to give away too much time because we're running out. The test is on Wednesday, and we haven't talked about the planets yet. Holy cow! We haven't talked about anything about the planets yet. We got the stars figured out. They rise and set 4 minutes earlier, and they move 30 degrees per month in the sun. Go ahead.
Are you going to give us a chapter 2 study guide?
I did. If Blackboard has them, you can just download.
When did you give them out?
Weeks ago. 2 weeks ago, maybe.
You're missing like 2 columns of us, I think.
Yeah, but the next day I came in and filled those
No,
in.
not the actual packet, because I only have, like, studied out chapter 1.
I passed them out. I know I passed them out. And if you don't have your copy there on Blackboard, you'll have to download it and got your, or you don't even have to print it. You can just look at it, whatever is easier for you. But yeah, I did give them all out. I tried to give them out a little bit ahead of time so you can have more time with them to study. And again, that's why they're on Blackboard, so that anytime you want to pull up the next study guide, if you're ready to move on. Planets. We haven't even talked about the planets yet. All we've done is map out all we've done is map out the stars and the sun. What about those planets? Remember, I think I might have told you this. The word planet means wandering star. Our ancestors realized that there were 5 things up there that didn't act like the sun or the stars. They wandered around. So we gotta fill those in. I'm thinking. We can do that Monday. Come with questions Monday, because if you have homework questions, right? You want to start looking ahead. You have a chance to ask me some homework questions for Monday or Wednesday, but Wednesday's the test day. You don't want to be taking too many questions on test day. Yes?
Are they gonna be like complicated algebra?
No. No math. No math. Nope. No math. Nope. All right. Let's close up shop. Have a good weekend. Have a good week, whatever. Leave your homework somewhere. Make a pile. Start a pile, please. Make a pile. Excellent. Yeah, make a pile.